Let's talk about protein now. First of all, what is a protein? Proteins are made up of amino acids. There's 20 amino acids that are made up in protein, and different combinations of amino acids will make different proteins. The same protein will have the same order of amino acids, but different amino acids in different orders will create different proteins. Everywhere from our hair to our muscle to our skin, there's protein in our bones, appetite, and so forth. Many of the enzymes, or all the enzymes in our bodies at least, are made up of some proteins. And also we have other factors such as hormones and so forth will have those in us. Antibodies is another big one. And so methionine happens to be the first one always, but then after methionine there'll be just different structures of amino acids. Here you can see the basic structure of amino acids. So if I turn on my pen here, you can see I've got 4 different amino acids listed here. This R stands for the functional group, and that would be different for every amino acid. So this is just the basic structure and how they bind to each other in order to make that. So again, there are 20. 10 of those amino acids are considered essential or indispensable, and that just basically means that most mammals cannot make them at all or cannot make them in sufficient quantities to meet the demands of growth or whatever is going on. And then there are 10 amino acids that are considered non-essential or dispensable. These ones we have to be careful. That doesn't mean they're not required for making proteins. It's just that if they're not, we don't have enough of them in our diet, we can make them ourselves. Okay, so that's very important to understand that. Interestingly, the microbes in the rumen, they can produce all 20 amino acids from other amino acids or from ammonia and other carbohydrate sources that they get. So they can make all 20. So theoretically, you could feed a ruminant animal 0 protein in its diet and it would still be able to survive as long as it had a nitrogen source and the carbohydrate sources it required. What are those amino acids? So the essential amino acids, the easy way to remember them is by using the acronym PVTIMHALL. PVTTIMHALL. So you have phenylalanine, valine, threonine, tryptophan, isoleucine, methionine, histidine, arginine, leucine, and lysine. Okay, and then the non-essentials there are alanine, asparagine, aspartic acid, cysteine, glutamic acid, glutamine, glycine, proline, serine, and tyrosine. Again, any combination of those amino acids, particular one will give the particular amino acid structure and give every protein its own uniqueness. Here's this diagram again. Now this time it's with ruminant nitrogen use, and again, one of the things we have to be aware of, I've kind of alluded to this already, is that we have, so we get the nitrogen, we get grains and forages. We can also get what's called non-protein nitrogen. Again, the bacteria can use non-protein nitrogen in order to make, that gets broken down to ammonia. And then if the energy is available, the bacteria can grow and we can get bacterial protein. The protein itself, some of it will escape the rumen, okay, and go directly to the intestines, and some of it will be broken down by the rumen microbes, either back into ammonia or into bacterial protein. And then that bacterial protein, when those bacteria die, gets brought to the intestines where it's digested down to the amino acids, and then those amino acids are absorbed and they can go through into to the liver, okay, through that portal vein again. If there's proteins that are bound up in things like ADF or in lignin that cannot be digested, those will be undigested and go right through into the feces. So coming back here, any ammonia, if there's way too much nitrogen in that rumen and not enough energy for them to make that bacterial protein, the ammonia will escape as well. When it goes to the liver, it gets made into urea. That urea will have a few different fates, if we could say. It could go to the kidney where it gets urinated out, or it could go to the mammary gland and becomes milk urea nitrogen, or it can actually be recycled back through into the saliva, okay, back through the saliva, back in urea, and come right back into that rumen for a second chance. That's important, okay, because we can actually use that to our advantage when we're feeding our sheep, especially our maintenance ewes. So again, then the bacterial protein will again break down, and then they come to the protein and it gets absorbed. And then in the liver, they can either be released as amino acids to go either towards the muscle for muscle growth or for milk protein production or for many other functions that exist, or they can actually be broken down. Some of the amino acids, most of the amino acids can be broken down and made into glucose as well. They're gluconeogenic as well. Now, sometimes, I'm sure you've heard the term crude protein before, And so if you were to take here you can see again that basic structure, and you notice that there's some nitrogens here, and some of the R's, what would be off here would be nitrogens as well. There'd be some nitrogens in there. And so if you actually figure out how much nitrogen compared to the total weight of that protein that exists, it's around 16% of nitrogen is, 16% of protein is nitrogen. So therefore, if we take, if we have a sample that we analyze and it has 3% nitrogen in it, okay, like I have as an example down here, I can divide that by 1/16, or divide that by 0.16, right? Divide it by the 16, multiply it by 1/16, or that's the same thing. 1 divided by 0.16 is 6.25, so we can just take that 3 and times it by 6.25, and we'll find out that it has 18.75% crude protein. Keep in mind, that's a crude measurement of protein. Okay, because for example, let's have a corn sample, and I do just that. Let's say this is an alfalfa sample. I take an alfalfa sample and I analyze it, and it comes out 18.75% crude protein. If I now go and get some urea, which isn't protein at all, put that into the alfalfa, mix it up in there in the ground alfalfa, send it off to get analyzed, there's going to be higher levels of nitrogen in there now. They're going to test it. It's going to come out maybe 24% crude protein. Have we increased the protein levels at all? Not at all. We've actually just increased the nitrogen in there. So remember, crude protein is a crude measurement. To give you an idea, urea, for example, is 45.5% nitrogen, which would mean it's like 284% crude protein. I'm being a little bit facetious when I put this next one down, air. Air is 78% nitrogen, so theoretically, air is actually 487.5% crude protein. Obviously, neither of those are going to be sufficient in order, because they're not true protein at all. Now we have hair, for example, is another example though. Hair is 15% crude protein, so that means it's 15% nitrogen, and so 94% crude protein, and it is a true protein. However, just because it's a protein doesn't mean it's digestible. Hair is very indigestible, and so it would be a very, very poor protein source for our animals. Then we have something like soybean meal, which is 7.8% nitrogen, comes out to about 49% crude protein, and that's a highly available one. Distillers grains, we've already talked about that. That's a byproduct from the ethanol industry, about 4.6%, and so it's going to be around 29% crude protein. Corn, about 1.3%, and it turns out to be about 8.1% crude protein. Besides crude protein, then we can also have something called metabolizable protein. This is true protein. Anything that's metabolizable protein is actually protein. It can come from feed. So for example, like that soybean meal it'll have also some non-protein nitrogen in it as well, but it has true protein in there that's actually metabolizable by the animal, and also the ruminal microbes, mostly the bacteria, very highly nutritious source of protein for the ruminant, and so it's around 60 to 65% crude protein in bacteria, so a highly available, highly digestible, metabolizable protein. Okay, and that is the amount of protein that's actually absorbed by that small intestine. So if it's in the feed and it actually gets absorbed by the animal, then that would be considered metabolizable protein. I already kind of alluded to this as well, the soluble protein or the non-protein nitrogen. So really I should start at the bottom here. Non-protein nitrogen is not true protein. For example, urea is a non-protein nitrogen. It's usually they're very soluble in the rumen fluid, so when the animal eats those, it's very quickly available for those microbes. Again, you should start thinking, if I'm going to have this energy available in the rumen so quickly, or so this nitrogen available, I better have some energy available as well. Otherwise, it's just going to get recycled back. And remember, that process of making urea in the liver is very energetically expensive. So we want to keep that very efficient by having a protein and energy source that match each other. Then we have soluble protein. It may or may not be true protein. It might be, for example, even amino acids and so forth. It's easily soluble in the rumen fluid. And again, it's also very rapidly available to the rumen microbes. The next category that we would talk about is degradable intake protein. Degradable intake protein does include the non-protein nitrogen and the soluble P, but also includes other proteins that can still be degraded in the rumen as long as you give it enough time. Okay, the amount that actually gets degraded on depends on the feed, the type of feed it is, how mature the feed is. So for example, more mature alfalfa is going to be less degradable than less mature alfalfa. How you treat the animal in terms of the feed. So for example, when you're drying distillers grains, if you dry it under a high heat and you dry it aggressively, it's going to become more undegradable. It's going to become less degradable. And the other factor, of course, that makes a difference is the animal. What's the passage rate of the feed in the animal? If that feed is going to spend an hour in the rumen, you're going to get a certain amount degraded. But if that same feed were for some reason to stay in that animal for 2 hours, you're going to have a whole lot more of it degraded because it's just spent more time in there. So the passage rate, for example, increases when an animal's lactating versus a dry, but it also can change based on your chop length. You chop something really fine, you're gonna have a higher pass rate than if it's longer as well. How do we measure this? How do we find out what's degradable intake protein? We do that by using nylon bags. So we have a rumen cannulated cow, for example, and we'll get these, they look like little tea bags. We'll put those tea bags, actually I have one, a small one right here, okay, you can see that. It's like a wee little tea bag. You put the feed sample in there, you seal that in there, you put it in the rumen, and I'll put some in over many different times. I'll put those feed samples in there, take them out, weigh them, and I can see how much of it disappeared over that time and get an idea of the degradation rate. And then once I learn what the passage rate is, then I can find out how much of it's actually going to end up being used. There's also in vitro, which is like in the laboratory methods of analyzing it as well. Then we have undegradable intake protein. This is protein that escapes the rumen. It goes in the rumen, it just doesn't get broken down either fast enough, maybe if it spent longer time in there it'd be fast, or it's completely undegradable to the ruminant. Sometimes you'll hear this referred to as rumen bypass protein. I don't really like using the term bypass because bypass makes it sound like it skips, doesn't go through the rumen and misses it. It actually still does go in the rumen. Rumen escape protein is a legitimate term because it escapes the rumen, again, over time. This may still be digested and absorbed by the animal, okay? So that protein is, and again, some of the soybean meal will actually escape as rumen escape or undegradable intake protein. And then in the stomach, in the abomasum, okay, it still gets digested down to the amino acids, and then it can be absorbed in the small intestine as amino acids there as well. Some, however, also will just not be digestible and will end up going right through into the manure. I like this diagram. This diagram really kind of shows it well. Here you can see on this side I got the feed, I got non-protein nitrogen like ammonia and amino acids. If I have carbohydrates available, okay, then the bacteria can make the protein out of that, or the amino acids go directly into microbial protein. Soluble protein is going to be available for those microbial proteins. Some of this DIP, another way you can you'll hear it sometimes referred to as NDFIP, so neutral detergent insoluble protein. And so some of that protein will be degraded in the rumen if it spends enough time in there. Some of it will not, it will escape. And some of it may actually land up going right through into the manure, not being used. And then you have ADFIP. Some of that ADFIP probably it's going to be difficult to be used. Some of it could still be used by microbial protein. Maybe a wee little bit will be available in the abomasum and small intestine, but most of it's going to pass right through into the manure, and we're going to lose it. Okay, and then again, those amino acids, whether it's microbial protein or whether it's protein that was able to be broken down and digested after the rumen, will get broken down into amino acids and get absorbed into the blood. This is just another way, and this one here, one of the ration formulation programs I use for dairy cattle uses this fraction terminology, and you can just kind of see how the fractions A, B, B1, B2, B3. So A is always going to be available in the rumen, B1 is almost always going to be available in the rumen, and then B2 is mostly available, B3 maybe not so much, maybe some of it will go on, and then they're just making the assumption that all the acid detergent fiber is being rumen escape. So the last slide I have here, I just want to talk about, so what affects how digestible that protein is? Well, again, the source. And again, being facetious, putting hair versus soybean meal, but I could do distiller's grains versus distiller's grains. One ethanol plant might use a more aggressive system for drying it. And what actually happens is then the proteins actually will start binding to the sugars that are in there, and you'll get caramelization. And so it looks like a darker brown or darker yellow color versus a lighter yellow color. It's going to be less degradable, less digestible in that rumen, and more rumen escape. Maturity, again, early bloom alfalfa is going to have more NPN, more soluble protein in it, whereas more mature alfalfa, it's going to be locked up into that ADF fraction. The processing, I kind of mentioned that one already. The heating, again, makes it more UIP. And then again, passage rate. If the longer it spends in that rumen, the more opportunity it has for the bacteria to finally get it broken down. And so if I can, so depending on what my purposes are, and this is something, again, that's a little bit tricky for people to understand, is increasing the passage rate, I can actually get more nutrients into that animal in a day, but it may end up being less nutrients per pound of feed. Okay, so if that passage rates increase, it's not going to get the same percentage of feed. If that feed spent 2 hours in there, it can digest this much. It's only spending an hour in there, well, it's only going to get this much out of there. However, I can put more feed in there now. I'm getting like 3/4 of it, but now I can eat twice as much food in a day, so I'm going to end up actually getting more feed, more nutrients total into that animal. And so as a producer, you always have to weigh those two things. You have lots of hay, chop it a little finer, you'll get more nutrients out of it, but you're going to burn through more hay to do that. All right? If you're short on hay, leave it longer stem and let it be the scratch factor that you're for your diet, and then you can feed the other nutrients that they need with byproducts and so forth. So again, there we get just a very short introduction into protein, what crude protein is, what metabolizable protein, what the true protein is, and the important fractions to understand is non-protein nitrogen, soluble protein, the degradable intake protein, and the undegradable intake protein.